Hello, fellow. My name is James Owusu-Appiah, and I believe in innovation and doing things differently. This video has been prepared for you to guide you through some well-known concepts that will aid your studies and preparations towards exam. Due to COVID, we cannot meet in person to discuss, so I hope this video finds you well and helps you achieve excellence. Thank you.
Hello guys, my name is Mano Utabel and today we are going to talk about the Eulers formula and the Eulers identity. Remember that this is a gateway initiative to help demystify various complex concepts into simple and understandable form to students. Now let me mention that the Eulers formula and the Eulers identity form the heart of complex number analysis. Named after the Swiss mathematician Leonhard Euler, the Euler's formula is a mathematical formula in complex analysis that establishes a fundamental relationship between trigonometric functions and the complex exponential function. So basically, the Euler's formula just establishes a relationship. It tells about how the trigonometric form of complex numbers relate to the exponential form of complex numbers. So we are going to see how the formula came about and how we can maneuver our way around it. The formula simply states that for any real number x, where e is the base of the natural logarithm, I is the imaginary unit, and sine and cos are the trigonometric functions which we already know as sine and cosine respectively, with the argument being theta given in radians. Now let me mention that the argument of a complex number is defined as the angle that the complex number makes with the positive real axis. Positive real axis. And the argument is also measured in the anti-clockwise direction, in the counterclockwise direction. So we can see it from this side. This is e to the power I theta, where e, as I said earlier, is the base of the natural logarithm. I is the complex unit which we already know as the square root of -1. Theta I just defined as the argument, and we are relating this to the trigonometric form of complex numbers. And so the relationship I just talked about is equal to cosine of the argument plus I multiplied by the sine of the argument. And let me mention again that the argument is usually, and to be on the safer side, used in radians. So you'd have to convert your argument from degree mode to the radian mode. Now this formula is very common in mathematics, physics and engineering, and it is very useful as well. And so we are going to see how it came about and then also get a way to manipulate this formula to our own benefit when we are analyzing complex numbers. The Euler's formula was obtained by comparing the series expansions of the exponential and trigonometric functions of the e, which is the Euler's number or the base of the natural logarithm, cosine and then sine. So let's see how Euler came about with this formula. And like I mentioned, it is as a result of comparison between the series expansions of e, sine and cos. So let's talk about the series expansions of these functions. So we can see here sin x given in the series form as x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial, going on and on and on. And beneath it is the cosine function, which is also expanded in the series form as 1 minus x squared divided by 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial, also going on and on. They are series functions that add on to infinity. And the last one we have is the expansion of e to the power x itself, which is also given as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power 4 over 4 factorial, also going on and on. And so We are going to derive a relationship between these three and see how the formula came about. So take note of the various expansions, and from the way it appears at the moment, you can see some relationship between these expansions. Now, in the third expression we have down here, if we are to replace x with ix, where I is the square root of -1, that is our imaginary number that we know. If we are to replace that x with ix in the expansion of e, which is the Euler's number, we are going to come out with a very beautiful expression, which when compared gives us the Euler's identity, the Euler's formula. And so let's see how that came about. Unfortunately, this isn't clear enough for us, but let's see. So we are replacing x with ix in the expansion of e to the power x, and if we do that, you would see that all the exponents that are 2, 3, 6, 7, and so on would yield negatives, because I to the power these numbers would have negatives in them. And if we are to vividly expand and group like terms, by grouping like terms, I mean that terms without I would be on one side and terms with I also on the another side, all separated by brackets. You would see that we get in one bracket 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial, going on and on. And in the second bracket, we get I multiplying another expansion, which is x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial, also going on and on. And from the previous analysis that we have done, you can tell that the expression in the first bracket is the expansion for cos. Let me go back for us to see. So if you check very well, you see that for cos you have 1 minus 1 over 2 factorial multiplying x squared. So simply we have the denominators to be factorials of even numbers, and the powers of x are also even numbers. And let's see how that appears in the first bracket. Yes, so we can see that in the first bracket the same thing happens, and so that means that the expansion in the first bracket is that of cos x. And from the same way, we can see that of the expansion in the second bracket is that of sin x. Let's also see the expansion of that as well and compare. So for sin x, we have x minus 1 over 3 factorial x to the power 3, also going on and on. And as in the same way, we can see that the denominators are factorials of odd numbers, and the same applies to the exponents of x. They are also odd numbers. And so let's see how that appears from the Euler's expansion. Yeah, so we can see that the coefficient of I, which is the whole expansion in the bracket, also appears to be the expansion for sine. So we have x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial, also going on and on. And so this simplifies to give us that if we are to replace x in the expansion of e to the power x with ix, where I is the square root of -1, we are going to get cos x plus I sin x. And Euler was the one who came about with this formula, and so it is named after him as the Euler's formula. And out of the Euler's formula came the Euler's identity. The Euler's identity was just derived by replacing x with pi. So the formula is giving us cosine of x plus I sine of x, and this is equal to e raised to the power I x. Now let's replace x with pi, which is 180 degrees in radians. That gives us e raised to the power I pi is equal to cosine of pi plus I sine of pi. Now, we know that cos pi, which is cos 180 degrees, will give us -1. And sin pi, which is sine of 180 degrees, would be 0. So that clears the imaginary term from there, giving us e raised to the power I pi is equal to -1. And if we are to write this expression beautifully, we are going to get e to the power I pi plus 1 is equal to 0. And this nice expression we have here is also known as the most beautiful equation in mathematics. And you can Google search that and you would get that as the output. So this is what we have beautifully here, the Euler's identity, or the most beautiful equation in mathematics. And it is called most beautiful because, as you can see, it combines the 5 unique numbers in math into one equation. E, as we all know, is a very unique number in math, the base of the natural logarithm, and I as well, square root of -1, which we haven't seen before, but we keep imagining. And by the I is our own pi that does not want to get rational. And then comes 1 and 0. You can see that all these are unique numbers that mathematics cannot do without. And so combining them into one equation yields something very beautiful to mathematicians. That's why they call it the most beautiful equation in mathematics. And in the next video, we are going to manipulate and massage these two formulas into something very useful to us. And like I said, the two of these two, that is the complex formula and the Eulers formula and the Eulers identity, form the heart of complex numbers analysis. And personally, I would say that they can help solve over 90% of complex number questions. And so we'll see how that can be done in the next video. My name is Owusu-Appiah Emmanuel, and I'll see you in the next video.